Welcome everyone. It is 6 p.m. and it's time for the Server Room show. This is episode 19. Thank you for SDF Public Unix SSD for hosting the server. This new show is recorded and broadcasted live at Unknown radio station every Saturday at 6 p.m. UTC time. There is a voice over IP phone line active during the show. You can call it either from regular phone or via SIP. The number is +1 910 665 9191. The SIP account to call in at is 261414 at San Jose 2, like in the number 2.voip.ms. I would like to thank for everyone who tuned in today and also the people who listens to this in a form of a recording, or perhaps the people who are watching this live and twitch.tv link provided. I would like to say that as this is a live show, all the blobs and errors are left in, no cuts, no buts, it is raw material. Because I hardly receive any feedback, I made sure that I left all the contact details to get in contact with me in all actual and previous show notes. You can find them on unradio.net website under the DJs tab, and you just go to the server room show tab, and there you can find all the previous and actual episodes, and on the very bottom of each of them I placed the contact informations, which about the email and this voice over IP line, and also where you can download the previous episodes in a higher quality in FLAC, in lossless form, in case you couldn't listen to the live broadcast, or perhaps you don't want to grab the MP3 from Unknown Radio archives and you would prefer something in a higher definition. This is a part 2 from the episode we did last Saturday on episode 18 regarding microservices, Docker and Kubernetes. That was part 1, and now it's time for part 2. We talked about previously the differences and the advantages and disadvantages of monolithic architecture versus microservices architecture. We nearly started to talk about Docker, but that was when the time ran out, so we shall continue from Docker. So if you followed the previous episodes, then we already spoke about Docker on episode 14 and 15, which was about virtualization, and you could have learned there that Docker is a type 2 virtualization in a form of platform as a service, which delivers software in packages called containers using the OS level virtualization. Another explanation what Docker is. Docker is an application build and deployment tool. It is based on the idea of that you can package your code with dependencies into a deployable unit called a container. Containers have been around for quite some time. I found one example of a text which was mentioning that perhaps container technology can go as far as back to Sun Microsystems when they developed it as part of Solaris 10 in 2005 as zones, or perhaps it mentions another example of text when I was searching for containerization and containers. Other sources noted the BSD jails as one of the first forms of container technology before it got into mainstream with in today's world regarding Docker. So as we discussed it about virtualization episode in 14-15, as many things sometimes not new under the sun, and they have roots way in our past. Like we saw, many of the technologies and terminologies regarding virtualization was coming from the roots of mainframes. That is a little bit similar about containerization or containerize something as small as a service or a microservice. Another explanation which I found that was describing quite clear what Docker is an open platform for developers and sysadmins to build, ship and run distributed applications, whether on laptops, data centers, virtual machines or the cloud. Containers are a way to package software in a form that can run isolated on a shared operating system. Unlike virtual machines, containers do not bundle a full operating system. Only libraries and settings required to make the software work are needed or required. This makes for very efficient, lightweight, self-contained systems and guarantees that the software will always run the same regardless of where it's deployed. This is the typical example of when developers say that the software X was running fine on my machine and I don't understand why it doesn't run on the client's machine. Containerization in this form takes care of this problem, because as long as it runs on the Docker engine on the container on the developer's machine, it will run exactly the same way, no matter where that Docker engine and where that container is being placed. It will work exactly the same way. So this worked on my machine and it doesn't work on the client's machine, it doesn't apply anymore. So this issue is gone. And yes, the software that hosts the containers is called the Docker engine. So let's see another piece which is important regarding Docker, which is called the Docker file. That's the piece of text file actually, which describes the build process for an image, for how to build a Docker image. So the Docker file is the text file which describes the steps and the required pieces to create an image, a Docker image, which in exchange, when it's being run, it becomes a container, a Docker container, which is a running state of a Docker image made from a Docker file. That's the best explanation. The people who looking at my screen could see that I have in the show notes a very simple example what a Docker file is. It's really describes from the beginning that, for example, let's say an application which will be based on Node, the files required to run is npm install and then npm run when the image is up and running. It can be automatically create an image and contains all the commands necessary to build the image and run this application. In the example on the show notes, it describes first that the base image should be Alpine Linux, using the available image from the Docker repository. Then it installs additional Python and pip applications. Then with the next command it upgrades pip and copies over some source files for the application, for the Python application in this example, copies them over from the host machine, copies them into the container. Then it runs the pip install copies some more files, and it exposes a port to be able to access from outside the container, and then it runs the Python application. It's a very simple Dockerfile example, but it describes that how can you put the pieces together, and you can specify your commands to make sure that your source files, or your if you, for example, running an Nginx container, that you copy over your source files for your website, or pieces of other source you need for whatever your container is doing. And as we said, the Docker container is the runtime instance of a Docker image built from a Docker file. So what other components Docker has, or Docker uses? As it's a service offering, software as a service, it has three main components. The software, the Docker daemon, called the Dockerd, is a persistent process that manages Docker containers and handles container objects. This daemon listens for requests sent via the Docker Engine API. The Docker client program called Docker provides a command line interface that allows user to interact with Docker daemons. The second piece is the objects, which breaks down to another three pieces. Docker objects are various entities used to assemble an application in Docker. The main classes of Docker objects are images, containers, and services. The Docker container is a standardized encapsulated environment that runs applications. A container is managed using the Docker API or CLI, which is the Docker command line interface. The Docker image, it's a read-only template used to build containers. Images are used to store and ship applications. Like we described, that a Docker file can be used to create a Docker image, which after, when you place it in a running state as a form of a Docker container, it becomes the container itself. And the Docker service, which allows containers to be scaled across multiple Docker daemons. The result is known as a swarm, a set of cooperating daemons that communicate through the Docker API. And the third piece is registries, which is the Docker registry. A Docker registry is a repository for Docker images. Docker clients connect to registry to download, or in another word, pull images for use, or they upload, push images that they have built. Registries can be public or private. Two main public registries are Docker Hub and Docker Cloud. Docker Hub is the default registry where Docker looks for images. Docker registries also allow the creation of the notification based on events. This is the registry where, if you specify in your Docker file, as you saw on the example in the first line, that it's set from Alpine to use as the base image, Docker will go up to the Docker registry, to the cloud, to see if there is an image with this name, and if yes, and you can specify version or other criteria if available, then it will grab it if it finds it, and it will use to create your container with the requirements you set. What tools are available in Docker? The two main tools are Docker Compose and Docker Swarm. Docker Compose, it's interesting in a sense that it allows multi-container applications to exist, because without Docker Compose, you could build and run one container at a time. You need to manually connect containers together, and you must be careful with dependencies and startup order, because if you think about it, how many times your single application only need and will only exist in one single container. Most of the time it needs additional pieces and bits and pieces. For example, if you run a website, you perhaps have an Nginx container which exposes the website, and you have additional containers, perhaps hosting the database part or some other bits and pieces. Without Docker Compose, you need to do all the connection together these containers, individual containers, manually. You have to be careful about the dependencies and sometimes the startup order counts as well. And this is what Docker Compose makes it easier for you to run multi-container applications. So with Docker Compose, you can define multi-container applications using a Compose YAML file. You can use a single command to deploy entire application consisting multiple containers. It can handle container dependencies. It works with Docker Swarm, networking, volumes, universal control plane. Docker Swarm is the second tool, which is, in the simplest words, it's Docker's open source container orchestration platform. So let's see now more about what is container orchestration and why you need it. So what is container orchestration? Container orchestration automates the deployment, management, scaling, and networking of containers. Enterprises that need to deploy and manage hundreds of thousands of Linux containers and hosts can benefit from container orchestration. Container orchestration can be used in any environment where you use containers. It can help you to deploy the same application across different environments without needing to redesign it. And microservices in containers make it easier to orchestrate services, including storage, networking, and security. Containers give you microservice-based apps, an ideal application deployment unit, and self-contained execution environment. They make it possible to run multiple parts of an app independently in microservices on the same hardware, with much greater control over individual pieces and life cycles. Some popular options for container orchestration are Kubernetes, Docker Swarm as mentioned, and for example Apache Mesos. Managing the life cycle of containers with orchestration also supports the DevOps team who can integrate it into the CI/CD workflows, which stands for the continuous integration and continuous delivery or continuous development. Along with application platforming interfaces, the APIs, and DevOps teams, containerized microservices are the foundation for cloud-native applications. So what the container orchestration platforms or tools can be used for? They can be used to automate and manage tasks, provisioning and deployment, configuration and scheduling, resource allocation, container availability, scaling or removing containers based on balancing workloads across your infrastructure, load balancing and traffic routing, monitoring container health, configuring applications based on container in which they will run, and keeping interactions between containers secure. So you can see that life is simple and easy as long as you only have, let's say, one host on which you have Docker running, and you run, let's say, one or two containers, and hopefully they're not multi-container applications. Then life in that cases are very easy. But when you have to think about just as a first step scaling of your, so let's say you have two containers, and they are not even multi-container applications, and they're just two containers. But the moment when you need to scale this either up or down based on the load or the volume you are receiving. You don't have a load balancing in place. Any scaling up or down you have to do manually, which means that you have to be monitoring and react immediately when the need arises, either to scale up or scale down. You cannot really do them with the scaling and this kind of provisioning. You can neither automate, you can neither make them with a single one-like commands. So then you can imagine that when it comes to multi-container applications and not one, not two, but let's say 20 or more containers, and you running it as part of an enterprise offering, then you see that you need a tool to automate all these hard labors, because otherwise too much time is being lost on managing things which you can automate. And all these things which we mentioned, container orchestration, is used for the provisioning, the deployment, scheduling, allocating the resources, being able to load balance and traffic routing, monitoring container health. It would be very, very, very hard to do it manually, even if you just had, let's say, two containers, two simple ones. So we mentioned that Kubernetes is one of the well-known container orchestration piece. So what is Kubernetes? Kubernetes is an open source container orchestration system for automating application deployment, scaling, and management. It was originally designed by Google, but now maintained by the Cloud Native Computing Foundation. It aims to provide a platform for automating deployments, scaling, and operations of application containers across clusters of hosts. It works with a range of container tools, including Docker. So Kubernetes can work with different underlying containerization engines or platforms or motors, so to say. And of course it works with Docker, which is one of the most famous between these platforms which are offering to run containers on top. Many cloud services offer a Kubernetes-based platform or infrastructure as a service, on which Kubernetes can be deployed as a platform providing this service. But also many vendors provide their own branded Kubernetes distributions. A Kubernetes cluster can be deployed on either physical or virtual machines. The people who looking at my screen can see that I have a quite good drawing I found about Kubernetes architecture. If we're looking at from the point of the developer acting, talking to Kubernetes through the master node, which contains the API server, which interprets the commands received from the developer. It can be done either from a command line interface, which is kubectl, or it can be done by the Kubernetes portal served by the master node. On this master node, you could also see that there is the etcd store, which stores your we described in the case of Docker that the Docker containers were built from Docker files. In the case of Kubernetes, the Kubernetes file what it describes is what containers I would like to run, how many replications I want to have at the same time. It describes the overall architecture, my desire, what I want to run, and how I want to run it on my Kubernetes cluster. So it could, for example, be a file, a Kubernetes file, which the developer feeds to the master node, and being stored in the etcd store database, which contains my wish, my desire, how I want my what is the environment I want to run on my Kubernetes cluster. Let's say that I want a Kubernetes cluster which consists of two containers. In this case, Kubernetes calls them pods. I want two Nginx pods hosting the same website. etcd database store this file as my vishent command, and it uses on the master node the controllers and the schedulers to execute this wish of the developer or my wish. It connects to each of the worker nodes, which are the hosts, on top of which, as a base layer, in this example which is on my screen, is the container runtime used is Docker. So there is a Docker engine running on each of my worker nodes, which are my hosts. So let's say two virtual machines, just to say as an example, running Docker container runtime. There is also a piece called kubelet on each of the worker nodes, on each of the hosts, which makes sure that the master node can talk back and forth to each of the nodes and give comments to them. There are also optional bits and pieces regarding the networking and UI, which lives on the worker nodes. Also the pods, which are the containers running on each of the nodes as per the specification in the Kubernetes file, as we mentioned in the beginning, being stored in the master node in the etcd database. And there is also on each worker node a kube proxy piece, which makes sure that networking and external access can be done. In this case, these serve as entry points for general users, because users don't interact with our cluster, what our cluster is offering, in this case an Nginx server we mentioned. They don't access this website through the kubectl command line interface, through the master node, or through the Kubernetes portal. Users interact with it normally in this picture you don't see, but I had some other ones in the show notes. Normally users interact to the Kubernetes cluster and its offering through a piece which called a gateway and load balancer, which can direct the request to the appropriate worker node on which in this case the example the Nginx server is serving the website, and it can take care of load balancing, or in case of one of my pods or containers of Nginx fails, it can route it to another one, and there is no interruption for users. I see that our time is up, and as again Kubernetes is not finished, so probably next time I talk a little bit more. There is a little bit left, and then we can go to another topic. So thank you for everyone for listening, and see you next Saturday.